title of my slideshow is Modeling Anisotropic and RAM Materials in Feko, an introduction to radar absorbing materials and their simulation. So this will include also a brief introduction to radar and radar absorbing materials at the beginning. So let me just start right away. So what is radar? Let's start with that. Let's start with the basics. What is radar? You can look at it as our eyes in the electromagnetic spectrum. So in principle, the principle is sending out electromagnetic waves and detecting their reflections. And that makes objects visible then. So the problem of reflection is that most objects are excellent reflectors of radar waves. They are easily detectable. So some people don't want that. So there is the need for stealth, and in many applications, mainly defense, but also specialized testing environments, or let's say here, these anechoic chambers here, right? So you want to get rid of these reflections as good as you can. So what is the RAM? RAM, it is radar absorbing material. And these are materials specifically designed to absorb incident electromagnetic waves, converting their energy into heat rather than reflecting them. As you see here on the right side, an incident wave and lots of stuff happening, and it does not escape from there. That's basically what you want. And how RAM works, of course, very simplified. There are different techniques, such as impedance matching, where you would gradually transition the wave from air into the material to minimize surface reflection, or loss mechanisms, where you would use resistive or magnetic properties in the material to dissipate wave energy, or interference, where you have structures where the reflected waves internally interfere destructively. Yeah, that could also work. Applications for RAM beyond military stealth. RAM is also used in anechoic chambers, like I already said, and reducing interference for electronic devices, and even in some consumer products. That's what I heard. I don't know any, but we just have to trust that. So what is Feko? Finally coming to Feko, our virtual lab for electromagnetic design. So why is simulation essential? Cost and time savings. Physically building and testing RAM prototypes is incredibly expensive and time consuming. Precision and optimization. Simulations allow for precise control over material properties and geometry, enabling rapid iteration and optimization. I actually did that in the preparation for the demos. I will show 2 demos a little bit later. And it gives you some insight. Feko provides detailed insights into how waves interact with materials, showing field distributions, currents, absorption patterns, which you wouldn't even be able to measure physically. Yeah, what is Feko? Feko is a leading commercial software for electromagnetic field simulation with various numerical methods like MOM, FEM, physical optics, where you're launching geometrical optics, UTD, and so on. Feko's role in RAM design. Feko is crucial for designing, analyzing, and optimizing RAM structures by accurately modeling complex material properties and geometries. And we will see how to do that. So, anisotropy, beyond simple materials, anisotropy. So, let's start with isotropic versus anisotropic, in case you haven't heard of that. So, isotropic, these are materials that have properties that are the same in all directions. Like, yeah, think of water. That's a good example. And anisotropic, these are materials whose properties depend on the direction in which the wave propagates or the field is applied. For example, wood. If you think of wood, which is, like it says here, stronger along the grain, or some composite material like carbon fiber or such. So why anisotropy for RAM? Well, there are several reasons. For example, enhanced performance. With RAM material, you are allowed for more tailored absorption, optimizing performance for specific angles of incidence or wave polarizations. It enables you to create thinner, lighter, or broader bandwidth RAM by precisely controlling the wave propagation within the material. Complex structures, many advanced RAM designs, for example, frequency selective surfaces, layered composites with specific orientations inherently exhibit anisotropic behavior. Some examples of anisotropic RAM: carbon fiber composites, or specific crystalline structures. So there's lots of things you may find here. Bringing anisotropy to life in Feko. So how do we deal with anisotropy in Feko? Let's go through the 4 steps here. First step, obviously, is to define your geometry, the geometric part that you want to apply the RAM properties to. And then second step, you define anisotropic material properties. So there's 2 ways, or 2 principal ways. So the first one is 2D. You can define anisotropic material in just 2 dimensions, where you apply different media to different directions. So you see that on the top right picture here. This is now just 1 layer, and I didn't enter anything. But you can imagine you have multiple of these layers, and you have then 2 directions, and you apply material properties, which you have defined earlier. And the other way would be the 3D anisotropic material, a little bit more interesting, I guess. And here is this is done using tensors. So there's different ways how to define a tensor. In my demo, in a 2 minutes or so, I will use the diagonalized tensor. And basically, just as you see for the 2D, also here you apply materials to the different directions, materials with their specified properties, of course. Yeah, step 3, then, of course, you define an incident radar wave as a plane wave coming from some direction or multiple directions. And then finally, you analyze the result in post-Feko. So let's see. I have prepared 2 examples for you. So the first one is just a basic RAM performance, and it's a simple metal structure. It's a flare structure, actually. And I compare the PEC version. PEC means perfect electric conductor, so no RAM involved, with a 3-layer isotropic RAM-coated structure. And I compare the RCS then. The 3-layer isotropic RAM, yeah, we will have a look at it in a moment. Then example 2 will be the anisotropic case, where I define a 3D anisotropic RAM material with some values that I found using optimization in Feko this morning, actually. And the interesting thing about example 2 is that I designed the RAM to be more absorbing for let's say for one polarization of the incident wave, and less absorbing, or actually not absorbing at all, for the 90 degrees off polarization of the plane wave. So let's see if we can do that. So demo 1, 3-layer isotropic RAM. So now it's time to start Feko. Of course, I have prepared something so we don't waste time. So I start with the setup of the 3 layers. I want to investigate how a certain stack up of layers behaves regards to the reflection coefficient. So look at that model here. Very simple. These are infinite dielectric layers, 1, 2, 3. They have a different thickness and they have different materials. You can see that by the color. All of that is set up using variables. Here are the thicknesses, T1, T2, T3, permittivities, and loss tangent. Here are the 3 media like 1 to 3. And with these 3, I define 1-layer structure. Actually, this is not used here. I forget what I just said. So this is not used here. Here, what we use are planar Green's functions, right? You already guessed it, I believe. So I went here to planes arrays, plane ground, and then here, planar multi-layer substrate. Here's where I define my 3 layers. For the last one, we have a background plane typical for RAM material. And then I apply the plane wave like this. Here we go. So it's looped over multiple directions, theta from 0 to 90. You can see it here. Just one polarization here. And the frequency is 10 gigahertz. And let me just run the model. It will just take 1, 2, 3, 4, 5 seconds or so. And that's really the quickest way to analyze RAM structures or RAM setups. Let me open post-Feko. So also these structures now, as you may already guess, they are very easy to optimize, right? You can now give the optimizer all the values, the thicknesses, like the permittivities, loss tangents, etc., and say minimize the reflection, and it will do it. And it will not take long, a couple of minutes maximum. Here we're in post-Feko, and this is the reflection coefficient, and you see for PEC we would have a clear one, and for this material it's not optimized. It's just more or less random values here. We have this sort of reflection coefficients. Now I want to use that RAM material for a real object. So let me open that. So you see the name is RAM thick because the layers have a thickness of multiple millimeters. Let me have a look at 2 millimeters, 4 millimeters, 6 millimeters, quite thick, 12 millimeters in total at a frequency of 10 gigahertz is more than a third of the wavelength. So we will take care of that a little later. And so this is the model I was mentioning, the flare with a size of 60 centimeters at 10 gigahertz. I will use RLGO in this case. And you see by the color, it is RAM coated. Let's have a look at the faces. You see 6 faces, and they're all packed with RAM coating. The RAM coating is the same that you saw in the previous model. And I compare this one here with a PEC flare without RAM material. And for that, I will just open post-Feko because I have everything prepared. And I have to carefully look at the clock time. Here is post-Feko. And you see the PEC flare gives you this RCS, the blue curve, and the RAM-coated flare gives you the green curve. So we have some decent reduction of RCS as expected. So without wasting your time, let's step over to demo number 2, anisotropic RAM coating. And again, let me open the prepared model. Here we go. Here it is. Yep. Yeah, it's the simplest model you can think of. It's just a metal square face, this one here, and on top we have a 3 millimeter thick absorbing material, and this absorbing material is designed as anisotropic medium. You see it here. Let's have a look how I did it. I chose the diagonalized tensor design version, and then basically you define dielectric media for the 3 directions, U, V, and N. And these media you will find here, you see. And you may ask, how did I get the properties here? Well, I just use an optimization. You see here. I won't run it now. So basically what I have 2 different excitations. Like this one is the X polarized plane wave, and another one is the Y polarized plane wave. And I wanted to make sure that for this polarization, we have a good absorption of energy, and for this, we do not. And that was my goal. So what I did is I set up 2 to optimization goals, like you see here. For the far field X, I wanted to minimize the RCS. And for the far field Y, I wanted to maximize the RCS. Yeah, I didn't even maximize it. It's more than PEC now. And the parameters are all that I have. The six properties of the three materials, and this gave me the values that you see here. And now let's open post-Feko to see the results, because we want to compare it with a PEC phase as well, and also we want to see some near fields. In this case, I not only calculated the RCS, I wanted also to see some near field reflections coming from that object to better understand what is reflected and what is not. So post-Feko is over here. So let's start with RCS. You see that the RCS for the X polarized plane wave is here, is like minus 23 dBsm, and for the Y polarized plane wave, it is what is it, 7 dB higher around about, or 7 dB less absorption, if you want to put it like this. Let's have a look at the near field. This is the near field for a PEC. If this was just a PEC plane without RAM, of course, then for both polarizations, the result, this is the reflected near field. Only the reflected near field is, of course, the same, just rotated. Now with the RAM material, it's a bit different. You see, this is the X polarized plane wave, and there's no red anymore. And this is the Y polarized plane wave, and here we have much higher values. So in other words, the reflection coming from that thingy here is much higher for Y polarized plane wave. Also, the other near field cuts here to give you that impression. This X polarized, Y polarized. Yes, and that's it. That's it for the demo. So let's return to those slides. There would be much more to say about RAM. I know that we have 15 minutes and just scratching surfaces here. So let's summarize. The key takeaway: RAM is vital for controlling electromagnetic waves, and Feko is an indispensable tool for designing and optimizing these advanced materials, especially when incorporating complex features like anisotropy. Future outlook: continued advancements in metamaterials, smart RAM, multifunctional stealth solutions, all driven by sophisticated simulation tools like Feko. And that's it from my side. Expecting your questions at the end of the session.